Now what we're going to look at are a few calculations involving conservation of linear momentum. The most important thing when you're dealing with conservation of momentum in these two lessons, whether it's linear or whether it's two-dimensional, is this diagram. This diagram, the before and after picture, will make or break your problem. It'll organize your information, it'll help you figure out basically what's happening in the question, and basically take that whole word problem, which is a bunch of numbers, and translate it into some numbers that you can apply to the momentum formula. So take all your information, put it down on a before and after diagram, and then the problem becomes way easier to deal with. What students tend to do is skip this first step and then get lost quite quickly in these types of questions. And these are considered to be the easy type in this lesson. In lesson 3, we're going to look at some very complicated where we're going to deal with multiple directions. So we got a 67.3 kilogram object moving north at 19.4 meters per second. Well, that's going to represent object 2. We have the mass of object 2 equal to 67.3 kilograms. Its velocity is going to be 19.4 meters per second. It's going to collide with a 45 kilogram object moving south at 23. Well, the mass of object 1 will now be 45.0 kilograms. The velocity of object 1 will be 23.0 meters per second. Now the very first thing is you've got velocities in opposite directions. You make a commitment at this point to make one of those directions negative. Most people usually choose direction up as positive, down as negative. If you want to do that all the time, go for it. It really doesn't matter. I'm not going to say north is always positive or south is always negative. When you choose one to be positive, the other has to be negative. So I'm going to make the velocity of object 1 negative 23.0. After the collision, the 45 kilogram object moves north at 4.3. Generally, these types of questions, the mass does not change. We're going to have conservation of mass. I've only seen one question in the whole time I've taught Physics 30 where you saw a change in mass, in the question. So that's not a common thing to see. Mass is always conserved. Moves north, and I'm going to use a little prime sign to indicate after for velocity. So the velocity of object 1 after 4.30 meters per second. Notice I'm going to put that in as positive because I chose up to be now positive. Object 2, the mass is the same, 67.3 kilograms. The velocity, what we're looking for, this is really what we're trying to solve in this question. Velocity 2 after is our unknown. So there's our setup of our information. The other thing that we're looking for here is to conserve momentum. Well, we know based on the formula that momentum equals mass times velocity. So we can deal with the momentum of object 1 before, object 2 before, and object 1 after right now. It's all the same calculation. The momentum of object 1 before will be equal to 45 times negative 23. So 45 times negative 23 gives me negative 1035 kilogram meters per second. The momentum of object 2 before equals 67.3 times 19.4. 1305.62 kilogram meters per second. The momentum of object 1 after 45 times 4.3 gives you 193.5 kilogram meters per second, and the momentum of object 2 after, we don't know. It's our unknown. So I'm just using the calculation P equals mv. Now on a written response, you should show one of those calculations, one substitution, and I'll do that on the next slide. The rest of the numbers can be written in after. It's the general rule we use on diploma exams. If you do a repeated calculation a couple times, then all you really need to do is show the substitution once, and then you can fill in the remaining numbers on the rest, and you will not lose any marks. So on the next slide, I'm going to do that. I'm going to show the calculation. Momentum of object 1 equals mass times the velocity of object 1. Momentum of object 1 equals, to go get my numbers again, 45 times negative 23. Put everything in proper units. The momentum of object 1 before was 1035, negative 1035 kilogram meters per second. Now, since this question isn't asking momentum, it's asking velocity, notice I didn't round to any significant digits at any point in here. I always go to appropriate significant digits at the end. Now, what we're going to do now is find the components, or sorry, the total momentum. So this little sum formula tells us that the total momentum before is going to equal to the total momentum after. That's all that big E-shaped symbol means. The sum of the momentum before equals the sum of the momentum after. Now, what a lot of students do is they don't even calculate each individual momentum. They will just go mv plus mv equals mv, which is fine. You can do that. But since I already know what these are, I'm going to go momentum of object 1 before plus momentum of object 2 before equals momentum of object 1 after plus momentum of object 2 after. And remember, my little prime symbol is representing after the collision, and I'm using subscripts 1 and 2 for the momentum of the object. Remember what we're chasing? We're chasing the momentum of object 2. So let's find that. Once we know its momentum, we can find its velocity. So we can go and manipulate for the momentum of object 2 after. That's going to be momentum of object 1 before plus momentum of object 2 before, subtract momentum of object 1 after equals momentum of object 2 after. We can put our numbers in. The momentum of object 1 was minus 1035 kilogram meters per second. The momentum of object 2 before 1305.62 positive 1305.62 kilogram meters per second minus the momentum of object 3 193, or sorry, momentum of object 1 after minus 193.5 kilogram meters per second equals the momentum of object 2 after. It takes a while to get used to writing this notation out correctly, But once you do, you'll get quite familiar with it, and you'll get your subscripts, you'll get your prime, and then you'll be very organized as a result. You just need to come up with a notation that'll easily separate before and after of your objects so that you don't confuse numbers. And if you punch this in, the momentum of object 2 should work out to be 77.12. So we get the momentum of object 2 after, doesn't look much like a P, equals 77.12 kilogram meters per second. Because it's positive, I automatically know its direction. I also know that the momentum of object 2 after will equal to the mass of object 2 times the velocity of object 2 after. So I can solve this for velocity. Velocity of object 2 after is going to equal the momentum of object 2 after divided by the mass of object 2. So if I take my 77.12 kilogram meters per second and I divide it by the mass of object 2, which was 67.3 kilograms, I will end up with 1.15 to the right significant digits, 1.15 meters per second. Now, because that's a positive value, remember in your original question you took care of the signs at the very beginning. Positive meant north, so you should state a direction, meters per second north. And we're done. There are other ways to solve this. Even sometimes I tend to do this a slightly different way. I'm going to show you on the next example kind of a shorter way to do this. Not calculating the momentums at the beginning, but actually plugging them into the formula. And you can choose whichever method you want. It's never going to go wrong to either calculate everything individually and put it into the formula, then go from there. Or if you want to combine a few steps to make this a little bit easier to work with, you'll see that when I do example number 2.